We usually only notice the power of electrical fields when they force their way into our macroscopic world, like when 100 million volts crack across the sky to strike a skyscraper. This was the starting point for early researchers. Benjamin Franklin and his contemporaries focused on these massive, chaotic electrical discharges. But to master the mechanics of electricity, physics requires us to strip away the chaos. We have to zoom all the way down and isolate the problem to a single theoretical point charge. A solitary charge resting in a void projects an invisible electric field. These vector lines radiate outward, pushing into space infinitely in every direction. Measuring the total power of something that never stops expanding is a challenge. To calculate the absolute strength of that field, we have to find a way to mathematically trap it. We build a Gaussian surface, an imaginary enclosed mathematical boundary projected into space to form a container around our charge. With a sphere, the distance from the center to the boundary is radius r. The total count of field lines piercing this container is electric flux. Calculating that total flux across a curved, three-dimensional surface normally requires complex calculus, but there is a more direct way to solve it. To simplify the geometry, we fracture the sphere into thousands of tiny, perfectly flat tiles. If we isolate just one of these microscopic pieces, we can identify it as our area element, delta S. On this scale, the electric field passing through the tile acts as a single straight line, our electric field vector, E. Every flat surface has a perpendicular angle pointing straight out from it, the outward normal vector, labeled r hat. Because our boundary is a perfect sphere, the electric field line and the tile's outward normal are perfectly parallel. The angle between them is 0, which collapses the trigonometry and removes the first layer of mathematical friction. The flux of our single patch is defined by multiplying the electric field and area element. From Coulomb's law, the electric field strength depends entirely on the center charge and the square distance to the tile. Substituting this into our equation gives a precise formula for the flux through this one micropatch. With the formula for a single tile established, we can determine the flux for the entire system by adding every tile on the surface together. Moving back to the macro, tiny flat tiles simply equals the total surface area of the sphere, 4 pi r squared. Now watch how the math interacts. The surface area multiplies directly against the denominator of Coulomb's law. The 4 pi r squared geometry of the sphere perfectly cancels the distance penalty. They vanish, leaving a simple result: flux equals charge over epsilon naught. The radius has disappeared from the calculation entirely. The distance to the boundary does not affect the total flux. If the radius is mathematically irrelevant, then the size of the container has zero impact on the energy we capture. A sphere the size of a marble and a sphere the size of a planet trap the exact same amount of flux. Since distance doesn't matter, shape doesn't matter either. The boundary can be a cube, a cylinder, or an asymmetrical mess. The total flux remains identical. No matter how you warp the container, every field line leaving the center must exit the boundary. This shortcut is Gauss's law. It determines total flux purely by looking at what is inside the container, bypassing the need for complex surface calculations. Gauss's law suggests a fundamental property of electrical fields. The geometry of the container is arbitrary. The only factor that dictates the total flux is the net charge enclosed within.